Alright, we're going to be looking at what is source degeneration in a common source stage. Let's first look at the normal common source, our good old friend common source amplifier circuit. I'm sure we're all pretty familiar with this, right? We've gone through it so many times. Alright, you know what, this is I think we're almost at the last leg of our common source videos. After this I might include just one or two more about source degeneration itself, but after that I think we're done with common sources and we can go into common drain amplifiers. I'm pretty excited about it. And alright, let's look at this one first. So, why do we need source degeneration and what it's all about? First of all, let's look at the circuit and let's figure out what the problem with the circuit is. I'm sure you know of a lot of problems, but I'm going to present one more problem here. Alright, sounds great, doesn't it? Okay. So, if you write the equation for drain current here, it is like this. Half mu n C aux times W over L, W over L, V in here, because it's VGS is V in, right? V in minus VTH, the whole squared. Understand this. ID depends, this is called the square law dependency. ID depends on the overdrive voltage. This is also called the overdrive voltage, right? So VOV. So this square law dependency on the overdrive voltage produces nonlinearity. How does it produce nonlinearity in the circuit? Now let's write the equation for gain, shall we? AV is minus GM times RD, right, for the circuit. And if you write these in terms of what they stand for, AV is the change in output voltage over the change in input voltage. Correct me if I'm wrong. As the negative of change in drain current for change in VGS, but again that is V in for the circuit, right? So RD. So look at this. ID depends on this overdrive voltage as the square of it, which produces nonlinearity, and V out depends on ID, right? So that's where we get our nonlinearity from. And a brilliant solution to this is brought about in Behzad Razavi's book, and it's called source degeneration. So what we do to this circuit right here is this. The top part remains the same. This is V in as usual, and here we add another resistance to the source of the MOSFET, right? And it's called RS because it's the source resistance there. So what will happen here is you have a current here again. As V in increases, your ID will increase, and so will the voltage drop across RS, right? So a bit of V in is spent on RS rather than just appearing as the overdrive voltage for the current, right? Rather than appearing there, a part of it is, a fraction of it is spent in dropping across RS, and that produces some linear results, Behzad Razavi says. And I think it's a bit confusing if you look at it that way, and trust me, I'm totally confused if I look at it that way. And he also presents another perspective to it. And let's look at that, and that kind of appeals to me better. So what he says is this effectively is GM, right? ID over Vn. So what he says is we have to make the output voltage A become less dependent or become a weaker function of GM, right? So it should not depend on GM as much as it is depending now, right? Because GM, effectively, GM is what is producing this nonlinearity. And if we make it a not a very strong function of GM, if we make it weak, we could definitely achieve some linearity. And we will see how we can do that. That's a pretty brilliant idea, actually. So when you compare these two circuits, first of all, this one, the top one, and the bottom one, I always say that the gain equation has the GM, the transconductance of the input part, times the resistance, the load resistance, as viewed from the output node, right? I always say that. So now in this circuit, the load resistance remains the same as it is RD, but that's where we're trying to do that. But here you have a different input structure. So GM would be different here, and it would be called capital GM. Okay. So for this circuit, just follow what I'm saying, and I think it'll make sense in some time. Alright, so the gain of the circuit can be written as minus GM times RD, right? Okay, and GM is what, effectively? Delta ID over delta V in, right? That's what it is. It's generally always that. But here, right? So in previous circuits it was just VGS, but here it's VN because we'll also be considering the effect of RS here. Okay, and ID can be written as what? From our small signal circuits, do you remember? GM times VGS, or we used to write VN there, it's also VGS, right? So I'm not sure how mathematically correct I am if I write this next step, but I think it's safe to assume this. Right? Correct me if I'm wrong. Right, the change in drain current. So we put that here. GM times delta VGS over delta Vin, and here we put a GM, right? The capital GM. Let this be equation 1. I mean, we've written a lot of equations, but for now, let this be equation 1. So in this circuit, right here, what can we write VGS as? VG, this is G and this is S right here, right? So how can we write VGS? Let's write that first. VGS equals VG minus VS, right? And VG here is Vin, right? The input voltage is what is the gate voltage. This for the source voltage, it is IDRS, right? That's what is getting dropped here, right? So it will effectively, oops, I'm sorry about this, the video getting cracked in between there. Alright, Vin minus IDRS, right? So this is pretty clear from the previous circuit. So we have VGS as this, and we need delta VGS over delta Vin, so why don't we differentiate this equation 2 right here with respect to Vn, right? So delta VGS over delta Vn, or del VGS over del Vn gives, with respect to Vn, when we differentiate Vn, we just get 1, right? Minus Rs is constant, and delta ID over delta Vn, right? So this is a golden equation that we can just directly substitute there, right? Delta VGS over delta Vn, and we have delta VGS over, oops, I don't know what's happening. Delta VGS over delta Vn there too. I think my computer is getting really slow. Alright, so let me just look what we have there. Okay, so GM can be given as GM times 1 minus RS delta ID over delta Vn, right? And this is equation 4. Now, this is a funny thing. This itself, the capital GM itself, is delta ID over delta Vn, right? If you go a bit before, if you rewind a bit, you'll see that for the circuit, right? It's delta ID over delta Vn. So we just need to manipulate this equation a bit to make it look pretty. There you go. So let's work on this further. Let's take GM to that side and kind of have fun. GM minus RS times GM, right? And this is GM. So we do a RS times GM, and here RS times GM, right? So we factor GM out here, We get 1 plus RS times GM equals GM, right? So capital GM equals GM over 1 plus RS times GM. I think this is equation 5, right? And for this circuit, let me do this real quick. I'm sorry about my dirty work there. So voltage gain is given by minus GM times RD, right? Now we can substitute this in place of this. So we get minus GM over 1 plus GM times RS times RD, right? So just think of what we have achieved here compared to this, right? We've made the we've made the output voltage, which AV is essentially delta V out over delta V in, right? So we've made that thing less dependent on GM and kind of dependent on GM and RS, right? And suppose in a case where RS is really greater than 1 over GM, okay? So if it's seriously great, what we can do here is kind of this term would be really big, right? So we can ignore 1 there. So what we get for GM over 1 plus RS times GM, right? And this term is really huge. Oops, I'm out of paper here. Let's go to the other side. Let me write that down for you again. Okay. GM equals GM over 1 plus RS times GM. So this is huge. So we can neglect 1 from there. So GM over RS GM. And this GM is gone, so it's 1 over RS. Voila! Just imagine. What have we got now? You've got minus 1 over RS times RD. Right? But of course this is an approximation. It is a reasonable approximation, not a very good one, but for the time being, we do whatever we think is best. So finally we have made the output voltage make it least dependent on GM, the small GM, right? Therefore, you don't have any nonlinearity. But think of the bad stuff that's happened here. Because we need linearity, we're sacrificing gain, right? This essentially, again, if you don't ignore the small GM, we have GM over 1 plus RS times GM times RD, right? So obviously this is smaller than what we had before, what we started with. So we're sacrificing gain. That is definitely there, but then we do get nonlinearity. And we even have a higher noise in this, but noise is something we'll cover later, but just to let you know. So that was it for now. We just saw source degeneration, how we can linearize the dependency of V out on of the circuit. All right, great. So keep watching videos. Thanks.